Okay, Lev, thanks. So we have Lev, Yakir, Wolfgang, and Artur. And let's try to make this interesting. First of all, I counted that you guys together have more than 200 years in quantum mechanics, no? without disclosing the age. So let's actually capitalize on that and ask you a few questions. Yeah. Hi, does it work? Ah, okay. Now? Better? Shall I repeat the joke? No, I was just saying that actually it's rare to have an event where I have 4 panelists. Together they have more than 200 years in quantum mechanics. So that's kind of... No, Yakir is by far. So I'd like to ask you first a few questions about that. And the first question is actually, with all your experience and in quantum mechanics, you know, doing research, what was the most surprising thing for you in this field? What got you surprised? And probably, Yakir, maybe you are the first one to answer this question, if you want.
Could you repeat the question?
Yeah, the question is, in all your, your working life in quantum mechanics, yes, what was the most surprising thing for you, if there was something? What was it?
For me, can you hear me? The most surprising thing for me was to see how much the fathers of quantum mechanics did not really understand it. And the more I thought about quantum mechanics, and the more I understood the kind of problems that were not resolved by the sort of experiments that the fathers of quantum mechanics considered, that was the big surprise for me, and I think I've made a big progress to try and understand it much better.
Yeah, but they didn't understand, but what did they didn't understand?
Sorry?
What was they didn't? You said you were surprised that they didn't understand,
Well,
but what was the point that they didn't understand?
Yeah. For example, they considered the issue of the two-slit experiment and the conclusion that if each electron exhibits interference properties, it must mean the electron is also a wave. And I have shown by the kind of new measurement that I discovered that I called weak measurement, that if I ensemble electrons and I assume they ensemble by weak measurements, that each one of them shows interference, nevertheless at the end I can find out on each electron through which slit it went. That means that there must be another way to understand interference. That's them saying that the electron is a wave. And the way is really by looking at the Heisenberg equation of motion and see that they have non-local aspects to them that shows that it's possible that while the electron goes through one slit, it knows, quotation mark, whether the other slit is open or not by the non-local equations of motion. And even though these non-local equations of motion exist, they don't violate causality because the only way you can find out all the properties is by pre and post selection. So, to conclude, people always thought that every measurement must disturb the quantum system. That is not true. If you have many replicas, you can do weak measurement, doesn't disturb any of the particles, and nevertheless, you can find all their properties. Using this weak measurement, you can discover a completely new phenomena that is related to pre and post selection and weak measurement, really very beautiful phenomena, and some of them, of those are already made by experiments all over the world, the quantum walk and super oscillation, and all of these are coming because it's very important when you have a mathematical theory to have also the right interpretation, because mathematics can answer any question that you ask, but it can never tell you which question to ask. So you must have a good interpretation, which is not mathematical, that will help you to find the right questions to ask. That's it.
Thank you. Lev? Okay.
Being a student of Yakir, in fact, I think what he taught me to look for surprises. And in quantum mechanics, there are so many surprises and so many paradoxes. But maybe the biggest paradox which I see today is why we have this big disagreement. I'm in complete disagreement with Yakir today. I believe everything is just wave, and it's behave locally, and it's very simple. But I don't understand why there is no this understanding among community of people working on foundations. We have more than 100 years of quantum mechanics, and we have so deep disagreement about what is quantum mechanics is about, how to understand it. And we have so many conflicting views which have many followers.
Do you think there is any experiment that can resolve this psychological dispute?
No, but mainly there are many ways to look at it. I think today one popular way to say it's so strange that we just shouldn't try to understand what it is. Among realistic interpretation, they cannot be distinguished by any experiment, although some people claim so. But I think there are some concepts, like I think determinism, which was very favorable before quantum mechanics, and quantum mechanics just led to people give up determinism, and lack of action at a distance. This led me to believe that everything is wave, because all other solutions don't have determinism and lack of action at a distance.
Okay, thank you. Wolfgang.
Do you want to go ahead, Artur?
No.
Oh, I have the microphone.
Yeah.
Well, surprises, that was your question. And I have to say I'm already surprised by what you said before, because that you can explain the double slit experiment with the Heisenberg equations of motion. That's a big surprise to me to hear. And is it published? That's my question.
Yeah, it's called Finding Matrix Cells of the two-slit experiment. I think it was published either in the PNAS or Physical Review. I don't remember.
I see.
5 or 6 years ago.
I see. So I have to look. I heard it from Adi. He was telling me about this once, but I didn't know where it was published. So I learned something. I still don't quite understand the non-locality in the Heisenberg equations of motion. I can see he reacted immediately when I said this now. But coming back to what is it that I was fascinated, of course, being a postdoc with John Wheeler many years ago, I really thought that the delayed choice experiment was something that fascinated me, that you can make a decision what it is that you measure, and you seem to influence the past. Today, of course, we would understand we make a measurement here, and it's that moment that is decided what property of either interference or particle nature that you see. It's the measurement here that decides that. If you ask me today what I find fascinating logarithmic phase singularities. I think Michael Berry has taught us so much about it, but there is an interesting connection between something well known since almost 100 years, the Landau-Zener transition, the rapidly non-adiabatic transition, and it's based on logarithmic phase singularities. Another effect, Hawking radiation, the creation of particles close to a horizon, an event horizon. If you really trace it back, where does this effect come from? It comes from a logarithmic phase singularity. All these effects. So third, the zeros of the Riemann zeta function. You ask yourself, where are they coming from? Make a guess. A logarithmic phase singularity. So it seems to be the same phenomena, but in different situations. So if you ask me, what is it that I find fascinating? It's the wave nature. In some sense, I agree with Lev there. It's the wave nature of quantum mechanics.
Okay, thank you. Artur.
Actually, you know, it's full of paradoxes. That's what I like about it. And I think two of them that I really, really like and made some impact on me are actually associated with Yakir and Lev. Yakir once gave me this puzzle where it goes roughly like this. You know, I give you a particle, it's a spin-half particle, and you can measure X or Y or Z component of the spin and give it back to me. And then I ask you, what was the outcome of the measurement, and then he will be always able to tell if you know, when I measure X, he would know the answer. If I choose to measure Y, he would know the answer. If I choose to measure Z, he would know the answer for sure. And how is it then possible, even though those variables are not compatible? So think about it. If you don't know the puzzle, it's beautiful, and the fact that the whole structure, mathematical structure of quantum theory has all those intriguing things is amazing. Another one was associated with Lev. It was Eliezer Vaidman famous bomb testing experiment. I loved it because it was phrased in such politically incorrect way. Thank you. You know, bomb testing. Later on, Lev, you tried to sort of tone it down and was like interaction-free measurement or whatever, but I like that one. And that is amazing. That's actually a scheme that, imagine that you have bombs with hypersensitive trigger, so that if you send even a single photon on this trigger, the bomb will go out. And some of the bombs, however, do not have this trigger. And you have a box full of bombs, and your task is to separate good bombs from bad bombs. And of course, you know, you cannot argue post factum. When it exploded, you say, oh, that one was good. That's not the point. So the point is you have to do it in such a way that you put it on a side and you know for sure it's a good bomb. And then the other surprise, like moving from mathematical structure that is full of surprises to, so those are like little puzzles, but they are so educational, so profound, keep you sort of like, keep your brain working during the night, right? So you really think about this. The other thing, like moving to more sort of a broader picture, for me, realizing that, for example, the Everett interpretation makes sense was like a shock to the system. You know, I thought for a long period of time that just, you know, many worlds, come on. But the fact, if you take mathematics seriously, really seriously, and don't talk about the sort of a mumbo-jumbo of classical quantum and so on and so forth, where you don't have a criteria where it is, that's the only way to go from now, at least. And the other thing is the peaceful coexistence of quantum and relativity, where somehow, you know, you can see that if we didn't have a random phenomena in quantum, then that would allow superluminal communication. And so this kind of a nice peaceful coexistence is another surprise that came as a, and you know, honestly, I can go on and on and on, that you don't want to hear the whole story, but it's just, if I were to choose any other topic for my lifetime research, I would still do quantum.
Okay, excellent. That's good for the students here. Okay, so everybody tells us that nobody understands quantum mechanics, right? I guess all of you guys heard that, right? Everybody tells you nobody understands quantum mechanics, except Yakir. Yeah, I know that you disagree. So what I want to understand is why people tell us that we don't understand quantum mechanics. What do we really need in order to understand it? And
Read my article.
Yeah.
I will.
Yeah, but I want to just first understand why people say that we don't understand, and second, what do we need to understand?
People say that if you look at the Heisenberg picture, there is no way to understand phases. So if I look at the AB effect, we have superposition of two separate wave packets, and in the middle there is a magnetic field that changes the relative phase. So it looks like a very nice picture in the Schrödinger picture to say here, there's some weight here, some weight here, the phase changes, local description by potential. But it's not local because you can't measure the phase locally. You can change the phase globally, and that will change the phase locally any place and not changing physics. So in the Heisenberg picture, I found that I can represent a vector in Hilbert space not by the wave of trivia, but by the question which observables, functions of S and P, have this vector as an eigenvector. And in this case of the two wave packets, I found that observables like functions of position, momentum, and powers of them cannot give you information about the phase. But there is this operator called modular momentum, or e to the IPL, which in this case, because of the fact that there is no possibility to do power expansion, in this case, the e to the IPL, the modular momentum, is an independent variable. And that modular momentum has no local equation of motion. You look at a potential V of x, the change of it depends on V of x where the particle is minus V, but potential a distance L away. So here there is an observable that tells you later what will be the local properties. Now it is a non-local variable and it has no local equations of motion, and then it allows you to say by pre and post selection that the pre-selection that variable was defined, the post selection tells you through which slit the particle went, and you can do in the middle of the ensemble non-disturbing measurements that will show you that each particle made interference, and nevertheless you know through which slit each particle went. And the issue whether the other slit was open or not is the fact that the equation of motion and this modular momentum are non-local. So I claim that the basic difference between classical and quantum mechanics is the Heisenberg equation of motion, and the fact that in quantum mechanics you have non-local equations of motion, while in classical physics all the equations of motion are local. And the reason why it's possible to have non-local equations of motion without violating causality is the uncertainty. The uncertainty allows you to have non-local interactions, and the only way to observe them is by looking at pre and post selection, and then you avoid the issue of violating causality. That is, in few sentences, the way to understand quantum mechanics.
So first of all, thanks. I should advertise that
I disagree with the statement that there is no way to understand quantum mechanics. I also disagree that you can understand quantum mechanics by just assuming the mathematics and telling that you have infinite number of worlds that you have never seen, you can never see. There is much better way to get rid of those infinite worlds. By realizing quantum mechanics, you need two boundary conditions, in the past and in the future. And the boundary condition of the future on our world gets rid of all these infinite family worlds, and you just select one of them.
Thanks. I should advertise that Yakir is going to give 3 lectures on that, which will be technical, and then you can understand what he claims.
Yeah,
we
will arrange it.
We are going to arrange it, but now except you that understands, what about the other guys?
I promise to give 3 or 4 lectures, and then no one will come out and say, I don't understand quantum mechanics.
Okay, Lev.
May I?
So people will say, we don't understand Aharonov.
Okay, Lev.
Some people understand me. I have an experimental proof. He doesn't.
So, first, I joined Yakir, and I'm not ready to say that I don't understand quantum mechanics. I'm not. I know that there are standard practice for teaching quantum mechanics. In the first lecture, to say that a professor tells, "I will teach you how to use it," but no one understands what it is. I think it's very simple. It's just a Schrödinger equation for universal wave function. Everett is right. But maybe I also have explanation why most people think that no one understands quantum mechanics. I believe I understand quantum mechanics. Yakir believes he understands quantum mechanics. We cannot agree about what.
But you don't believe the same thing.
We cannot agree about what is the right understanding. So when the people who even feel that they agree about quantum mechanics, they have completely different views. So the general public, of course, thinks that no one understands quantum mechanics.
I must say one sentence. There are two different ways of understanding. One is to invent a language that just in words say what the mathematics is. And the other is to have a language that is as free as possible for mathematics, because the basic sentence is mathematics can answer any question. It cannot tell you what question to ask. If you follow this guy, his mathematics does not tell you what interesting question to ask. But if you have a language that is free of mathematics, then you come out with interesting questions. And I think that if you follow my 65 years of research, you will see how my insisting on finding a question that is free of mathematics has led to many interesting new phenomena and new effects. So that's a proof. Okay?
Just a few. I don't say that Yakir's view is. I like very much his concept. He introduced non-local variables and find very interesting connection between them, which are very important. But I think the locality is very important. There is a local way. This is why I prefer another language.
Let's see. Do you want to comment on that?
Well, I think this is too far above.
No, you don't have to comment on the dispute. No, not on the dispute between local and non-local, and many words.
I tell you a very elementary problem I have, okay? And I cannot figure it out. And I don't even need Heisenberg equations of motion. So I must have been around 1870, there was Stefan and there was Boltzmann. Now, Boltzmann's first name was not Stefan, it was Ludwig. But Stefan was an experimentalist in Vienna, and he measured how the black body radiation depended on the temperature, and the energy density depended on the temperature. We know, of course, it's T to the 4. Now, Boltzmann derived this from electrodynamics and statistical mechanics. So, classical theories, electromagnetism and Boltzmann, and the Boltzmann constant. So C and the Boltzmann constant must enter. So if you would just by dimensional reasons compare energy density, temperature to the 4, you conclude that there must be a universal constant entering of the unit h bar, not h bar, but of an action. Now, because it's black body radiation, it must be a universal constant. So people, long before quantum mechanics came, could have understood that there must be some deeper theory behind it, because there's a new universal constant in there. Now, I'm asking myself, how come you can derive this formula except of a constant? The constant, the Boltzmann constant it's called, or no, the Stefan Boltzmann constant, that you cannot derive, because now that depends on 1 over h bar cube. And of course some factors, some numerical factors. You can only get that from the Planck distribution. And so I'm wondering, how come electromagnetism and thermodynamics could give you this formula that you usually only get from the Planck distribution? So it's a very elementary problem. And my suspicion is that maybe there is some kind of thermodynamics behind quantum mechanics. Because thermodynamics is the more basic theory of everything, in my opinion. And so maybe there is some derivation of quantum mechanics coming from thermodynamics. So I feel like from this old formula, we might learn a lot.
There is, by the way, it comes from information theory, but that's a discussion that we can have, but please.
Just to comment, I think that I like a lot what Yakir said, namely that mathematics allows you to answer a well-defined question within the formulas, but doesn't give you enough intuition to ask that kind of question. But I still have to side with Lev, because I think that, for example, the Everett interpretation as an intuition that guides you asking that kind of question or thinking in a certain way was very productive. My supervisor, David Deutsch, is quite clear about it, that it helped him to see the power of quantum computers, even thinking that the computations can be performed kind of in parallel in different universes and brought together by quantum interference. Of course, it's a very naive way to think. There are always, subtle things about it. But as a guiding principle, I think it's good to have good interpretation and be open-minded and prepared to change it. I also do not believe being guided only by mathematics. That's not very creative, not very productive, very useful from instrumental point of view, but certainly not creative. So you have to have a mental picture how those things work. And maybe the nature of human being is that you don't have to be even logically consistent in having this mental picture. You may actually switch from, if you solve one problem, you may actually be, it's like looking at a given object from a slightly different perspective, and depending what you want to paint and how you want to paint, with a bird's view or frog's perspective, that can be more useful or more beautiful. So I would be, the day we have experimental evidence pointing to some other interpretation they send the Everett, I'll be the first one to drop and follow that thing. But for now, I find it more aesthetically pleasing and useful from the creative point of view. And Yakir, I do promise I'll read your papers and try to think very carefully.
I'm not going to make a vote among the audience who will favor many world or not. It's very dangerous.
No,
but let's, yeah.
If I may just say, this is actually, the question you are posing are quite deep and profound in a sense. When you come to think about it, we have this 100 years of quantum theory, right? And nothing has changed. There's no progress per se. We have exploited it to the limits. We have quantum devices, we have iPhones, we have possibly very secure communication system, quantum computers. But then this all just goes from the theory that hasn't changed for 100 years. And in my personal opinion, one culprit is just wrong philosophy. It's simply the positivist influence and Copenhagen interpretation did such a damage to generations that we're not being able to ask the right kind of questions exactly. And I think maybe with quantum computing, trying to build it is the most sophisticated experiment that ever humankind decided to set up. Maybe we'll see deviation from the prediction. Maybe we'll be able to, with the help of computational complexity, computer science, find this deviation and make a progress. But I think one reason why we haven't made progress over 100 years is just probably that some of us went into cul-de-sac of wrong kind of philosophy.
Okay, that's an interesting point. Let's actually get down to earth, right? I mean, these companies are investing, I don't know, hundreds of billions of dollars to build these computers. From your experience, why do you think quantum computation will be better than classical probabilistic calculation? I mean, what's the evidence? Why would we do it?
You say so.
It's a tough question, so just give an epsilon answer. It's okay, but why do we build it? I mean, who knows? Why it's better?
No, we do know, right? So whether I think that computation is just, this is the mantra that you had so many, you're provoking, you know the answer, right? So the mantra is that computation is a physical process, right? It is. Any computation is a piece of the physical process. You prepare your experiment, call it input, you read the final state of the experiment as the output. So if computation is a physical process, then what you can compute and how efficiently you can compute depends on underlying physics, and we know that quantum can offer us different non-classical basic operations to which you can give computational meaning. And therefore, we know that whenever you make a progress, you discover new laws of physics, you base computation up on these new laws of physics, you have inherently new computation. So that's, this answer, right? And the thing is that with this, it cannot be any worse because it contains the old computation. It can only be better, and we have evidence, of course, that it is better, and in terms of computational complexity in particular. What is it good for is another thing, right? So which we can speculate for a while.
But let me ask you, is it possible that we can control all the decoherence processes in it? I mean, we're going to entangle more and more, and Are we going to control the
universe? The universe does, right? The universe calculates like that. So he's smart enough.
Well, if you believe in the Everett interpretation.
No, the universe does the calculations quantum mechanically, right? You enter the lab, as Artur was saying, you prepare something, you measure, that's a computation. It does it quantum mechanically. So he's arguing, oh, it works.
But then you could build an analog computer just based on quantum mechanics, on the Schrödinger equation.
But the quantum computer is just running the Schrödinger equation. It's a unitary transformation, right? That's
right.
what it does.
But you still have to keep all these subsystems unitary. And I'm not sure that you can do that.
Why not?
I have doubts on this nowadays.
Okay, why not?
But how do you control the coherence?
Because the universe is able to do it. Why we are not as smart as the universe?
I hate to disagree on this because the universe is not doing quantum computing.
But I don't want to monopolize this discussion, but we do know how to construct error correction and fault-tolerant quantum computation. So you might be right that if you want to control the subsystem and that subsystem interacts with the environment and therefore the evolution of the subsystem is not unitary, there are ways to bypass it. And we know we have the threshold theorem which says that if your components are designed and controlled with a certain precision and there's a threshold there, it doesn't have to be infinite, then you can have scalable fault-tolerant quantum computation. So in theory, there is no reason to believe that it's impossible. I know that in theory there's no difference between theory and practice, but in practice there is. But still,
luckily we are all theorists here, by the way.
But the fact is that there's no reason a priori why we cannot just build them. It's just terribly difficult but doable.
Lev, you wanted to comment on that?
In fact, I have to admit that I was and still somewhat pessimistic about quantum computer, which will be helpful to practical tasks. What I'm sure is that the technology develops from quantum computer, even today, is very helpful. So we'll get quantum sensing, we'll get precision measurement, we'll get everything else. So even if there will be no quantum computer with enough qubits to run something useful, the quantum, all this industry is extremely important, especially I think in this cyber issue. I am a little, I was more optimistic about quantum cryptography, which what we have today. And the money which we put into quantum computer will put, I think, quantum cryptography to the right thing, because it's exactly the same technology.
What do you mean? You mean QKD or you mean something else in quantum computing?
QKD, all this, yes, there's a QKD. I thought that there should be today in a stage that it will be cheaper to make a QKD system than classical cryptographic system. But this is not, currently, this is not what people use. I don't know if I can say something about the future. I think 10 years from now, the most security system will be based on quantum cryptography, not on classical.
Well, actually, that's a question to Artur. You know, the classical cryptographers, they are not happy with this answer because they typically tell you, even for QKD, you need an authenticated classical channel. And okay, so what did you do? You need a classical channel as well. So why don't you just use ordinary complex mathematical problems as post-quantum cryptography? What would be the answer to that?
Well, there are two components here. One is the community of cryptographers is roughly vaguely divided into two. There are hardcore traditional, no-nonsense engineers who know their profession really, really well tested in battlefields and so on and so forth. So they don't take kind of like esoteric nonsense as something, they don't take it easily, right? And then there are those guys who want to explore new directions, and going in the direction of quantum is just one of them. And it is a challenge for conventional cryptography, mostly because people don't understand it. It just takes some effort to get it, right? And But if they understand, then they think it's still, and here they are right, they think that it's still not mature enough to address all problems that cryptography is facing. And I think there's a need for some kind of a fusion of those fields. We should like each other more in this community because it helps to, because it's quite clear that in the future, I may not be on left side saying that all security system will actually use quantum crypto, but I think a lot of that, and there will be a hybrid thing where classical will coexist with quantum, and we need expertise of both. So all these kind of silly arguments coming from, which are mostly cultural, I would say. If you go to technical details, there's no disagreement so much. But it's just like, it's when you have a certain habit, that you work in the field for 50 years or so, and you are well-known and respected crypto guy, will you take easily some things that are so esoteric, and you still prefer to use your well-trusted solution in the real world? And I do understand and I respect this kind of view. I just only wish for a little bit more of open-mindedness on the other side.
I see. Okay. How are we doing with the time, actually? Okay. We can go again, very high above the ground and ask you, okay, 100 years of quantum mechanics passed. We achieved what we achieved. What will be the challenge for the next 100 years? What are we what do we need to solve? Or what we don't understand? Or what's the most important question?
Well, let me come back to one thing, because one topic you have not addressed at all is quantum sensing.
Let's go for quantum sensing.
Somehow before we go into 100 years...
Excellent, go ahead.
I would rather talk about quantum sensing, because
go ahead.
I talked about these cold atoms, and we can build gyroscopes out of it. And, we have a lot of possibilities to compete eventually with the gyroscopes that are based on light. And, of course, there are these companies in America that build atom interferometers, like, Mark Kasevich has big companies. Measuring G opens up, changes of G, and opens up, of course, a lot of applications, finding out holes in the ground and so forth. So that has a lot of potential for applications and for economic growth. And this is now, if you might say, fruits that we can grab right away. It's not far away, it's already there. So that's why I would say, and there are still lots of fascinating questions, like in an atom interferometer, how do you make the area larger? Like the rotation rate depends on the area that is enclosed by these beams. How do you make it larger? Now, in case of light, it's easy. You just have a glass fiber and you wrap it around. Now with the atoms, they go through it once, unless you use guided interferometers, guided atom interferometers. So I feel like even in this field, there's a lot going on before we go into the next 100 years.
Okay, excellent. Actually, I should add also materials. We didn't discuss quantum materials. It's another important topic, new phases of matter. Absolutely, you're right. So, yes.
And I have to say, I was fascinated by the talk on the phase transition induced by the measurement and the percolation. As I said, I find a lot of these cross work between different disciplines I find fascinating. So my feeling is that you're asking, are we going to make progress in quantum mechanics itself? I find it more fascinating to bring quantum mechanics together with other fields.
That's actually a question. With which fields?
Oh, as I said, in my personal hobby is, of course, number theory, quantum mechanics and number theory. So that's one of the things I find fascinating.
I believe that what will happen in the next 100 years, hopefully much sooner, is another revolution. I believe that our own experience are really critical experiments on the most complex system. Our brain is certainly the most complex system of that number of atoms that exist in nature. So we have a number of experiences that are supposedly connected with physics, but the physics tells us that our experiences are wrong. I mean, they are not true. For example, we have the experience that the present, now this present, is very different from the present yesterday and from the present that will be tomorrow, but physics doesn't allow us to talk about time in this way. Everything else is changing when time is changing, but to say that time itself is changing from one present to another doesn't make sense. So here is an example that we have a very strong experience that time is different than what the physics of today is telling us. That's one example. The other example is that when we look at the result of a quantum experiment, we take a Stern-Gerlach experiment, we can get a spot either at one place or another place. We see only one spot, but quantum mechanics tell us, no, that's wrong. Actually, you see two spots, but you're not aware of it. That is that kind of belief. So here's an example. We have a very strong feeling that there is only one world, but quantum mechanics tells us, no, you're stupid. There are practically infinite number of worlds, and in other worlds you may be suffering now, you may be the biggest billionaire, etc. So, second example, where there is a very strong clash between our experience and what physics is telling us. And the most important one is the issue of freedom. Quantum mechanics, although it allows uncertainties, tell you that those uncertainties behave according to the Bohr rule, and this is really the choice between different possibilities that are opened by quantum mechanics is random. It's not connected with the true freedom that we feel. So we have either to say that our feeling of being free is an illusion, or again, that something is missing in the physics of today. So I believe that there may be still another revolution in physics that will have to do with the parameter of complexity. We know that the revolution of quantum mechanics has to do with the sizes. The revolution of relativity has to do with the light speed. Perhaps there is another possibility of a revolution that has to do with the fact that all our physics of today is based on experiments that are done on simple systems. And we have only one set of experiments that are done on the most complex system, and that's all our own experience. So my belief is we should expect another revolution that will say that when complexity of the system is so big that there is no way to copy it, then something new can happen.
Actually, it's an interesting point because it's an interesting point because it's happening today. If you look at the AI revolution, that's exactly that. You take trillions of parameters.
But AI is a system that I can copy with it.
Yes, but it's trillions.
No way to copy my brain.
Yeah, well, that I don't know, but trillions of parameters give you an interesting emergent phenomena, like what we see in the LLMs. But
the AI machine doesn't have conscience and doesn't have free will, doesn't have real freedom. It's very complex, but it's a different kind of complexity, and the difference is that it has to answer the Bohr rule in our brain, because we can never copy it, and we can never do some experiment, doesn't have to satisfy the Bohr rule. That is the basic.
Okay, so it's clear that Yakir believes that there is free will. I don't know what about you guys, but Lev, do you think there is a free will?
I cannot define it, so I cannot say that I can believe in it. So,
what do you mean? You had a choice to come here today or not?
There is no. I was trying. I was reading Dennett, Elbow Room, other books. There is no. I couldn't find a definition, and when I don't have definition, I can. I don't.
You're escaping the.
Yakir tells me all the time that he feels sorry for me that I don't have a free will, that I cannot define it. But I don't. In fact, I also hope that against what Yakir just said about revolution. Just before quantum mechanics, physicists were feeling that they understood the whole nature. And they were very wrong. It was special theory, relativity theory, and quantum mechanics. I think today, every experiment we perform and we can calculate, they all agree. There is no one case when there is a disagreement. I see there is no any reason to believe that there will be any new revolution. There are some small things which have to clean up, quantum gravity and whatever, but I believe quantum mechanics is correct period. And there will be no revolution, and we have to feel well that we understand nature. And I hope it will happen during the next.
It's interesting that you say quantum gravity is a small cleanup.
Of something that, some experiment that we don't understand. What about the experiment that I tell you that I feel that this person is different from another? It's not an experiment?
I'm trying to work about Everett a lot. And then I assume Everett when the quantum mechanics only fully correct. And then I try to explain what a person, observer, who in Everett theory will feel. And I will see, he will feel exactly what I will see. There are many like me, but they will all feel exactly. I don't like many words. I would like to have one word. But I need parallel words to explain my experience here. Because if Everett is wrong, then there is action at a distance. And this, as a physicist, I cannot accept.
This we will not resolve here, but we have a couple of more minutes. So I mean, there are students, young researchers in the audience. Like one recommendation: what to do, where to go, in which field. What is an interesting question to ask?
Well, I think that's what you mentioned very briefly, namely the fusion of AI and quantum. It's just in two ways. AI may demystify the process of consciousness and human thinking. Maybe it's much simpler. Maybe it's not so enigmatic. Maybe it's not so mystical as many people think. Maybe it is like LLM of some kind. But so there are two ways I think AI can influence this. One is using classical AI to help us to do quantum, and that's already happening, even though at this stage it's maybe not so creative, but very useful. And the other one is what kind of monster can we grow up when we do the quantum training, right? So we have quantum computer running AI. There are issues with that, like RAM and so on. But suppose we can overcome the issues which are mostly related to feeding that quantum computer with experiences, the learning sort of thing. How an entity that grew up being taught up on quantum phenomena from the very beginning would tackle quantum problems. So that's fascinating to me.
That's interesting. Wolfgang.
The way I understood Yakir, you were really asking the question, what is time? I feel like that's really one of the questions that is pressing, because we go back, electrodynamics, Ritz and Einstein, they were wondering, where is the arrow of time coming from?
Yeah.
Now, Lev, just because we haven't found an experiment that disagrees with our theory doesn't mean it's not out there. It could well be out there, we just haven't found it. And of course it's difficult to look because we don't know where to look. But as I said, if you would ask me, and I retire in a couple of years, I have time then, and I can think about time.
Well, actually, I think we all agree that, thanks a lot. We all agree that time is the most important resource. Definitely before lunch. I'd like to thank you for this really fascinating panel and also you guys for listening. Thank you.